Good hello, CMPT 140 students. We're going to jump into our first chapter, which is all about algorithms and what that word actually means. I like to start this chapter off by imparting the best lesson I ever received about computers onto you. And that is that computers are incredibly stupid. It's not you, it is them. And I am qualified to say this. The biggest thing that you're going to be learning through this class is how do you communicate to the computer to get it to do what you want to do. And effectively, computers are like toddlers that only will listen to us if we speak to them in a very, very, very particular way. And that's usually through some sort of programming language. We also need to give them a very clear set of instructions for how to solve some sort of task. So that set of instructions for solving the task is what we would call an algorithm. There are algorithms that exist outside of computer science. We probably just don't call them that in our day-to-day life, but maybe you will start after this class, that we can use to do things like cooking. Say we have a recipe that tells us you need to get these ingredients, you need to combine them in this way, maybe cook them at this temperature, wait this amount of time, and then you can eat it. Last weekend, I had to put together a couple of IKEA dressers. Those came with algorithms. They're called instructions, but truly they were algorithms. And they told me, take this piece and put it together like this, and then make sure you're paying attention to this very small detail on this piece so you put it together correctly the first time and not the second or third time, because that didn't happen, of course. So we're going to get into what actually makes something like that an algorithm. What does that mean for a computer? And where would we see those examples in our day-to-day life? We have some exercises in this slide deck that you'll work through. Some of them I'll walk you through the solutions step by step. Other ones you'll go to the course website, you'll take a look at the solutions and you can compare there. I'll have some examples and some antidotes that I can use to kind of elaborate further on some of the information that we went over in the textbook as well. That should bring me to, I really should have started with this as my first point. Make sure you've read the textbook before watching this. The textbook is free. The textbook is great. The textbook contains all the information you will need to solve these problems that we're going to present. Anything I say is just repeated from the textbook to emphasize the point that we want you to learn, all right? So, as I mentioned, an algorithm is an ordered list with a set of actions, and it's used to solve a problem. So when you think about my IKEA example, my problem was I needed to build a dresser. I had a whole bunch of pieces that were not currently a dresser, but I knew if I combined them, they would become a dresser. And the instructions that came with that gave me my step-by-step actions that I needed to take in order to actually construct that dresser from all of those pieces. I was baking buns this weekend as well for Canada Day, and I have my list of ingredients that I had to get and the way that I had to combine them and the steps that I then had to take for making the dough, making the buns, how long the buns needed to rise, and then how long they needed to cook and at what temperature in order to get a bun out at the end. My problem was I didn't have buns and I needed buns, so I used that algorithm to solve my problem. And really what you'll be doing as a computer scientist is writing algorithms or instructions and ordered lists of actions to the computer so that it can solve problems for you. And that is the power of what we will be teaching you here. It is an amazing skill to have, and I hope you're excited to learn as I'm excited to teach. The key thing when it comes to actions and algorithms is that they have to meet these three characteristics that we talked about in the textbook in order for it to truly be an algorithm. So they have to be imperative. They have to be in order to do something. They have to say, for instance, say my problem was I am under-caffeinated and need coffee. One of the actions that someone might give me in an algorithm to solve that problem would be pick up your coffee cup. Okay, now take a drink. Ah, excellent. Coffee. Amazing. Those are all definitive actions that if someone gave me, I would be able to do. Which brings me on to the next point. They need to be feasible. And the feasibility of that action is going to depend on whether or not, going to depend on what your audience is. Is it a computer you're talking to? Is it your prof? Is it a toddler? Is it your dog or your pet? The feasibility of those different things or the actions that you give will depend on the audience you're giving it to. I wouldn't be able to tell my dog to pick up a coffee cup. As much as I would love to train it to get and fetch me coffee as I sat here throughout the day, it would not be feasible for it to do it. Likewise, the computer cannot fetch me my coffee cup. I have to do that. It is feasible for me. The other thing that would make something maybe not feasible for the different audiences is it self-explanatory? Does the audience understand what needs to be done? For instance, same example. I know what you mean if you say, hey, Kim, pick up your coffee cup and take a drink. My dog for sure does not know what that means. My nephew, who's 2 years old, he does not know what a coffee cup is and probably shouldn't be trusted to pick one up. And the computer definitely does not. So we're going to be working through a couple of examples in this next exercise here, of determining whether those three things are satisfied by various actions that were given. So for exercise 1, we're going to have two audiences that we're thinking of. An adult human, so like yourself or me or whoever you want to think of, or a computer. We have 5 different actions, and we want to know, does it meet all of those 3 criteria? So as a reminder, is it imperative? Is it feasible? And is it self-explanatory for an adult human or for a computer, I should say. So we'll go over a couple of these. All of the answers to them are on the course website, so you can take a look there as well. But here's the first one. Oh, and I should have my sunglasses for this. What a shame. I did not prepare appropriately. But do these sunglasses make me look cool? Is that an action? What are you thinking? This is where I miss our live lectures. I'm getting at least some head bobs here. I'm getting maybe a couple comments or something. What do we think? Would it be a reasonable action for a human or for a computer? Well, let's think about it from the computer's point of view. Is this asking the computer to do anything? Is it picking up a coffee cup? Is it providing a picture, downloading a file? Or is it an opinion? I think it's an opinion. It's not imperative. It's not imperative for the computer. And spoiler, it's not imperative for the human either. Because it's asking for an opinion. And truly, who's qualified to make that opinion call or that judgment call? Not me. Maybe you can make the argument that you would be. But at the end of the day, it's not an appropriate action for an adult human or a computer when we're talking about it in the context of algorithms, because it's not imperative. When we go to the second one, B, go swimming in the pool. Oh, okay. That seems imperative. Yeah, that's an action that I could do. I know how to swim. I know what a pool is. Okay, so probably a reasonable request for an adult human. If I tried to tell my computer to do that, though, I don't think it would know what I'm talking about. I don't think a computer knows how to swim, which would make it infeasible and not self-explanatory for that audience, right? And then we move on to C, read data from the USB drive. You give that to me as an imperative command? It is imperative. It is a command. But as a human, I'm not going to know how to do that, other than maybe plug it into my computer and get the computer to do it. But I'm not going to be able to read the ones and zeros from it. The computer, on the other hand, yeah, they are probably going to be able to handle that. You plug it in, it automatically does all of that stuff for us already. So probably reasonable for a computer, unreasonable for a human, unless we want to clarify that you need to use the computer to do this tasks, which maybe we would need a little bit more information on, and we'll get into that in the next chapter. What about D? Compute the sum of 5 and 2. I can do that. It's 7. I got this. I'm feeling good about myself over here. I could ask my computer to do the same thing, open up my calculator app, plug in those numbers, tell it to do that. It could do it. So it's reasonable for both humans and computers. It's imperative, it's self-explanatory, and it's feasible. Perfect. Our first win-win for both scenarios. And then we have E. Search for the best rubber duck on the internet. Well, when we think about it for a computer, they might not know what a rubber duck is. We would probably have to tell them, provide more details. So not quite self-explanatory when it comes to a computer. And when we think about it from the human point of view, what does best mean? We're going to get into a whole philosophical debate about what best means. We need more information on that too, so really not self-explanatory in that sense either. So probably inappropriate for both an adult human and a computer as an action. If you have differences of opinions on any of these, please put them in the course chats and we can chat about them more, or come to any of our help hours and I'd be happy, me or the TAs I'm sure, would be happy to talk to you about them more. What about exercise 2 here? Write an algorithm for using a stapler to staple pages together. There is an example of an answer in the solutions. Your answer does not need to look like this in order for it to still be correct. There's a lot of color that comes around when we're doing exercises like this and writing what we would call pseudocode. If you don't remember what pseudocode is, go back to the textbook and reread that section to remind yourself what that term means. We can come up with all sorts of algorithms to achieve this. What you want to do is go through the different actions in your algorithm that you wrote out and say, are those imperative, feasible, and self-explanatory? For if you were explaining it to a human adult, okay? If I was to write an algorithm for this, it might be something like, collect papers that you would like to staple as my first step. Why don't we open up here a notepad? See if I can get this going. Oh, I can just write on here, I'm pretty sure actually. Bear with me for a second. So here we go. I'll just make sure that this is recording properly. Awesome. Collect papers you want to staple. Wow. And now you're getting the real life view into my typing abilities. So here's our first one. So say maybe I'm in my office, I need to go around and got a bunch of papers here. I want to staple them. I already gave away maybe what the next thing I want to do for my task is. I went like this. Started to try to line those up to get them aligned in some sort of fashion to make it a bit easier to staple so that everything goes through the same staple at the end of the day. So maybe my next step would be align papers. Great. So I have my stack of aligned papers, and now what? I'm just waiting for my next task here. Where's my stapler? Locate. Stapler. Okay. Okay, let's see. Maybe in another drawer, do I have a stapler? Victory is mine. I do. All right, so I got my stapler. I got my aligned papers. Now what? Put papers into stapler? Now these won't all fit in my beautiful stapler that I have. But we'll put some of them together. I'm refining my algorithm as I go here. So we got some papers aligned into the stapler. Okay? Now, staple. It didn't work. Why? I'll put these two tasks in here that I just said while you think about why that might not have worked. Put aligned papers in stapler. Press down on stapler. Yeah, should have got me a stack of wonderfully stapled papers. There was one thing in my beautiful algorithm here that I forgot to check. Do I have any staples in my stapler? Spoiler, I don't. And I have none in my drawer, I already know that. So I'm going to be forever unable to complete this task. But maybe we want to make our algorithm a little more robust. So after we locate our stapler, we want to check to make sure there are staples. And maybe we want to add one of those control statements we talked about in the textbook. If there are no staples, then add staples to stapler. And you can see how we can continue to kind of iterate and make this bigger and better and more explanatory for our users. We can add different bits in. We can add things like those control statements in. And we can come up with all sorts of algorithms that would help someone use a stapler to staple papers together. And like I mentioned, there's a different example that's in the solution for also valid solution. If you'd like to post your solution that you came up with on the discussion board to see if it would be considered correct, feel free. But remember, when you look at it, you want it to have those imperative, feasible, and self-explanatory tasks that the user of your algorithm could actually accomplish. All right? I have so many typos in this. Oh well. All right. I'm going to leave you to do exercise 3 on your own. There's a solution for it in the PDF that's on the course website. If you want, I would encourage everyone to post their solutions on the discussion board. We can look at different solutions, talk about pros and cons of different approaches, and see what's going on. You're going to need some of those control statements that we talked about in the textbook, as well as just showed with the stapler example. So remember, control statements, as a quick refresher, they're a way that we can either indicate to do something if a certain condition is met. So you could think about it if we were going outside, you want to say, okay, if the weather is snowy, put on a winter jacket. Otherwise, we're not going to need to do that. So we might have some if statements, which we'll get into more later on. Maybe some else statements, so we'll either do this or this. We might have some repeating statements, so we'll say while or as long as a screw isn't tight while Kim is putting together her IKEA dresser, keep on twisting. Don't stop twisting until that screw is in place, right? So here's an example. I want you to get out a WordPad or some sort of text editor on your computer, and we're going to follow this algorithm. It's a very simple algorithm. All it's saying is that you need to watch me while the instructor's hand is up. You will write your name on a piece of paper. Okay? We're going to try this once or twice, and then I have a question for you after. Are we ready? 3, 2, 1. Let's go. Okay, let's call it done. I feel like I got too excited and rushed through that quickly. I want to know, how many times did you write your name on the text editor? Was it once? Twice? More than twice? What do we think? I know I raised and lowered my hand twice, so I'd assume probably maybe about twice. At least twice you got your name written down. If you have a short name like me, would you have written it 3 times? Let's think about this. Here's my example for me. Let's assume that I'm a student in this class. I'm also the instructor. It's very confusing. Hand goes up. I start writing, Kim. Well, my task is done. And then I check. Is the instructor's hand still up? Well, yes, it is. I guess I gotta write my name again. And is their hand still up? Well, yes. So another time. And I'm still doing my task, but their hand is still up. I guess I need to redo that task and redo it and redo it and continue and continue and continue. And oh, finally, it's done. With our control statements, anything that's indented underneath that condition of whether it's like while something is a certain way or if something is a certain way, the whiles will get done over and over and over and over and over again until that condition is changed. The ifs, if it is sunny outside, if it's rainy outside, bring an umbrella, only get evaluated once. So there's going to be, I think, 3 different types of control flow statements that we'll learn about in this course. 2 of them are what we would call loops. So those are going to be things like while loops or for loops, where everything that's indented is going to get repeated until that condition is met. And then we're also going to have things like if statements, where we only check that condition once, and then we change our behavior based on what that condition actually says. Was it a true condition or a false condition? And we're going to start introducing these. We're starting to introduce these concepts now so that when we introduce them again later on, we're already a little bit familiar with it, okay? So you don't need to master the terminology quite yet. The key point is that we have these things called control flow statements. They can be things like loops, where some set of tasks get repeated a number of times. Or they could be things like if statements, where we do one set of tasks if a certain situation is present, or a separate set of tasks if it's a different situation, okay? And when we're writing these things out in pseudocode, we always want to have our initial control statement, followed by anything that's indented that we either want repeated or done if it was a certain situation. Those things would get indented. And the indentation isn't necessarily as important for humans, but it will become imperative when we move into actually translating this into a programming language. So it's a really good practice to get started now, and it will be a requirement for whenever you're writing things like pseudocode on exams or assignments or different things like that, to make sure you're maintaining that type of structure, okay? All right, for our next algorithm or exercise, we're going to look at some different algorithms. We're going to identify the problem that's trying to be solved and some possible inputs of that algorithm and outputs. So typically, algorithms will have inputs and outputs. Think about me building my IKEA desk. My inputs were a whole bunch of wood scraps, screws and various things. And the output was a built, fully functional, 3-dimensional dresser, right? The same thing goes for computers and other algorithms we deal with and that we'll come up with. There's usually some sort of input that we're providing and then an output that we get at the end of the day. All right, so I'll just go through one of these and then I'll want you to go through the other one on your own and you can take a look at the solutions. And if you have questions, again, post in the discussion. But here's our first algorithm. If we read this aloud, it says, for each student in the classroom roster, call out student's name. If student does not stand up, write X by student's name. So first, before we get into the actual question for this exercise, I want to call out the 2 types of control statements we have here. We have a for statement, where everything that's indented underneath, so lines 2, 3, and 4, will get repeated until we've completely gone through every student in the classroom roster. That's the condition we're looking at here. We also have an if statement. So that's saying, okay, if this condition is met, so think if it's raining outside, then we're going to do something special. But we're only going to do that special thing if this one condition is met. Okay? So that is indented further. That one special task we have. We could have more tasks under that if we needed to. But for this case, we only need the one. And even though it's indented further than all of these other things underneath the for statement, it's still repeated within that for loop, in that control flow, okay? So every single time. So now that we've gone over that, when we look at this algorithm and think, okay, what problem is this trying to solve? I'm thinking attendance. Remember when I was in elementary school, this was very common. We'd have a substitute teacher come in, they'd have the class list, and they'd call out each student's name and usually absolutely butcher the pronunciation of a few of them. And whenever your name was called, you had to say here or present, or in this case, the expectation would be that when the student's name is called, they would have to stand up. And if they didn't respond in the way that was expected in the classroom, then they're not there. And we put an X by their name to mark that they're absent, okay? So that's for sure the problem we're trying to solve here is find the absent students in the class. For inputs, well, we probably need a classroom roster, right? That's going to be the list of all of the names. We'd also need a class of students. Otherwise, you'll be just like me sitting in your office and reading lists of names out into the abyss, and hopefully somebody on the YouTube machine is watching this, right? So ideally, this type of algorithm would be happening in front of a classroom of students. And we have to write on this class roster that we have. So we probably need some kind of writing utensil. Otherwise, it's going to be very difficult to write that X if we needed to do, right? So those are the maybe three things. Maybe you can think of some other things that we would need in order to actually execute this algorithm. Once this algorithm has completed, well, we would have a class roster sheet with X's next to the names of absent students, right? So one of our inputs would be getting slightly transformed by this algorithm, and that would be our output. There's some other examples of algorithms here. I'd like you to go through the same exercises and thinking, what is the problem? What would be some of the inputs? What could be the output or outputs? And checking your answers against the solution that we provide on the class website. Okay? All right, that's it for algorithms. We will get so much practice with algorithms in the lab and in the assignment coming up this week. I'd recommend that you read the next chapter. I believe the first lab is chapters 1 and 2 combined. So read the first chapter if you'd like, or you can jump into the first questions for lab 1 if you'd like to practice. If you have any questions, please, please, please make use of the discussion boards or the help hours or tutorial hours. That's what we're here for. We're here to help. Don't just struggle through this alone. It's a whole new language and a whole new world you're learning. So reach out for help when you need it. All right? We'll see you in chapter 2.